Hi, Priya. Priya Najang. Hi.
Hi, how are you?
Great. I think everybody is already here. We can start at 9.
Yeah, 13 minutes more, right? Yeah.
Hello.
Oh, hello. Yes, we are set.
Yeah, so we are all ready. We are set. Rafael, can you share me the YouTube stream link, or is that in the mail?
I'm going to ask.
Yeah, Libo, can you share because
Libo.
there could be questions which will come up on that also. Oh, thank you. Duduzile has shared it. Okay. Because there could be questions which would come on that link, so we'll need to follow that and see if there's something being asked there. Okay, yeah. Okay, good. That's kursi meri hai. I'll just move these clothes. ठीक है सर.
The students are here. We have a meeting room at the library. No, they already have the ones that registered for the course. They got I sent the same email saying if you are online, you get to the Zoom meeting, or otherwise, if you're in Brazil, to the library. And I asked the guy at the library to keep an eye in case he can just call me.
Okay.
Do you think maybe we can go to the library to take some pictures?
Sure, no problem at all.
During coffee break, perhaps?
Yeah. Outside.
Yeah. And then
We can do that.
Yeah.
We have a coffee break at 10:30. The library, I can just see it from here. It's very close.
Yeah.
Mm-hmm.
Yeah. You can see them in face. And then at lunch, what we should do, we should have lunch with the students. And the students pay lunch for us.
I think that's probably.
Rafael, is your location library? Somebody's asking.
No, I'm on my office with the people that are going to present.
No. Somebody has asked that for those attending in INP, where is the venue?
I sent a map. The library is
No, just look at the chat box. Look at the chat box.
okay.
Hello, Shanshan.
Hi, morning.
Hey, how are you?
Yeah.
So the Shanshan, the panel discussion, right? We'll do it more like a Q&A, right?
Yeah, but the prayer sound is not.
No, I'm saying for panel discussion in the end.
We need one. Yeah, I can hear.
You turn the volume on?
Now can you hear?
But I don't.
The ones that are not going to present must mute. So
I muted everything now.
Hi, prayer is on mute.
No, now I'm fine. Now I'm good.
Okay.
Can you hear me? Can you hear me now? Can you hear me now?
I don't hear. Hello.
So Shanshan, is Alejandro is also there, right? So the welcome, even
Yes.
Alejandro and Rafael can be with us, right?
Yes.
Yeah.
Well, together.
Yeah, so we can all do the welcome business. Yeah.
Yeah. We can all do it together.
Yeah.
Yeah.
Okay. Okay.
Priya, are we ready to start?
Yes,
we are all ready.
Yeah,
Okay.
we are ready.
I'm going to just do a short introduction and let's just go ahead with that's a lot of things to talk about today. So
Yes.
welcome everybody. Welcome everybody to there's a workshop on the VO, the AI in vitro observatories, transforming astronomical discovery. That's part of the 11th annual BRICS Astronomy Working Group workshop that's happening here at INPE in Brazil. We have a day of talks about AI in VO. Hope you all enjoy it. People that cannot watch everything, it's going to be on YouTube later. So let's just go ahead. The first talkers are going to be Priya Hassan and Najam Hassan. They are going to talk about vitro observatories and the goals of the workshop. So welcome everybody, and let's start. Priya, it's up to you. Thank you.
Thank you, Rafael. But first of all, we'd like to introduce our team. We have Najam Hassan, who's here with me. We have Shanshan Lee, who's present over there offline. And we have Alejandro and Rafael. Please all put on your videos. All of us can introduce ourselves and say hello. Shanshan, would you like to start?
Hey, hello everyone. My name is Shanshan Li, and I'm from China National Astronomical Observatory. And yeah, and I'm also working. I'm working at the National Astronomical Data Center, and I'm also responsible for the International Virtual Observatory Islands Education interesting group. So welcome everyone, and welcome. Very glad that you're interested in the virtual observatory and the AI technologies of the astronomy, and hope you can learn something today. Yeah, welcome.
Thanks, Shanshan and Alejandro.
Let me unmute myself.
Yes.
Hello
yes,
there. My name is Alessandro De Roclite. I am from the Centro de Estudios de Física del Cosmos de Aragón in Spain. And you may wonder why an Italian working in Spain is here. And I am a member of the Brazilian Virtual Observatory since a few years now. So working with Rafael and with Paula Coelho on VO education, research, and infrastructure. And I've been working with VO protocols and science for about almost 20 years now.
Great. Rafael, what about you?
I'm Rafael Santos. I am the head of the education division at the Brazilian National Institute for Space Research, INPE. I like the concept of VO. I've been trying to use that, but I don't have too many opportunities to work on that directly. So I'm glad to be here to learn rather than explain anything. Thank you.
And Libo.
Hi everyone, my name is Mulebohar Kulani from South Africa, and I work in astronomical observatory, and as well as taking, and well, I mainly work on the BRICS partnerships, and very glad to be here. Thank you.
And Duduzile.
She's not here. Sorry, so I was the one joined as Duduzile. She's not here.
Okay, fine. Then there's Najam over here.
Hello, I'm Najam. I'm a professor of mathematics and astronomy, and we have been using VO a lot as a teaching tool. And I hope this session too is of help to all of you. By the way, Najam means a star, and my name has brought me to astronomy. So, hello, everyone. Should we start?
Yeah, and I'm Priya. I also teach at the university in India, and or use it as an educational tool. So the first talk we have is an introduction to the VO, right? So we'll start with the talk on introduction to VO, after which we'll move to AI. People are welcome to ask questions on the chat window. If you'd like to, if it's very urgent, you can put up your hand and we can stop and answer your question, or you can put it up in the chat window. Similarly, on YouTube, you can put your question there too. We'll be checking that also. Yeah, thank you.
Yeah, so virtual observatory. Astronomy has changed in the past few years. If you look at astronomy in the past, you see that you have a very data poor science. Most of the records, if you look back, were either hand drawn. People looked through the telescope like Herschel and Galileo and so on. You see on your screen. The Pleiades constellation as drawn by an observer. You have sun with the sunspots. You have phases of Venus drawn by Jupiter. And there are certain maps. Each time they saw Jupiter and its moons through a telescope, they would just note it, see it, and plot it. But times have changed, and now we have a tremendous amount of data coming in. We have very sophisticated images. We have multi-wavelength observations of objects, which amounts to terabytes of data. Compare the image which we have of Pleiades here and the Pleiades which we have here. Earlier, they would think there were only 7 to 14 objects, but the numbers have gone up tremendously. Today, we know that they are confirmed at least 1,000 members. So with this, we are now living in an era of multi-wavelength astronomy. There are various ground-based and space surveys ranging from gamma rays, X-rays, ultraviolet, optical, and infrared to radio bands. And this has brought astronomy to the era of big data. Astronomical data is already amounting to petabytes and increasing with the advent of new instruments. And astronomy has evolved from hypothesis-driven, data-poor to a data-rich science. We are living in an exponential world. Astronomers have a few 100 terabytes now. 1 pixel, 1 byte per square second, which amount to 4 terabytes. We have multispectral and temporal data leading to 1 petabyte or more. Astronomers look for new kinds of objects all the time. There are more interesting ones, quasars, and so on. There's density variation in dimensional space, which the data gets captured. We need to do correlations in these undimensional spaces, and the data is doubling every year. And this data, as you all know, is also being made public and making it accessible to everyone. So, big data in the context of astronomy, I would break them into the 4 V's: volume, variety, velocity, and value. So there's tremendous amount of data in terms of volume which is coming in. If you have seen this, I'm sure all of you have seen this first image of black hole, which was used using Event Horizon Telescope observatories at the center of galaxy M87. This required almost 5,000 terabytes of data, which requires 44 years to upload on a standard internet connection and 22 years to download it. So we need different techniques, different ways of data and doing our computations. In terms of volumes, as I said, the story goes on. We have DFOS, the Palomar Digital Sky Survey, which amounts to 3 terabytes of data. 2MAS, the 2-micron All Sky Survey, to 10 terabytes. GALEX, 30 terabytes. SDSS, 40 terabytes. Vera Rubin's observatory is expected to have 14 terabytes per day, which is 50 petabytes per year. And LSST, the Large Optic Survey Telescope, about 200 petabytes expected, and SK, the square kilometer array, amounting to 5 terabytes per second, which is 400 petabytes per year, and amounting to almost 4.6 exabytes of expected. When you look at the variety, astronomical data comes in terms of large range of variety. We have images, we have spectra, we have time series data, simulations data. The data is saved in catalogs or in databases, and the data from sources are made available in different formats. Each data item often has more than thousands of features. So we have these catalogs with thousands of entries in each. And data have many different types. It can be structured, semi-structured, unstructured, and mixed ones. Coming to the velocity in the terms of the speed of producing and transmitting of data and analyzing data has become very important. LSST expects it will find 1,000 new supernovae each night for 10 years, which implies that at least 10 to 100,000 alerts will be requested. And the value of this data, so much of money is going into these surveys, into building up the ground-based large telescopes or having the space-bound telescopes. So the value is of immense importance to the astronomy community to discover new phenomena, discover new objects, understand our universe better. So it has much value to us. So the present scenario in astronomy is we are living in a multi-wavelength era, and there are data over millions of objects, allowing us to discover significant patterns from the analysis of these rich and unbiased images, catalogs, databases, and understand complex astronomical systems by comparison of data and numerical simulations. So various tasks which astronomers would be interested in is classification of spectra of stars, galaxies, quasars, supernovae, photometric classifications of galaxies, stars, and quasars, morphological classifications of galaxies, classification of solar activity, to look at photometric redshifts of galaxies and quasars, do regression analysis with that, study stellar physics parameters, measurements, to detect outliers, which are sometimes extremely important and interesting, and do these time series analysis. The answer to handle such large amounts of data across a large community of interested astronomers, amateur astronomers, and students is virtual observatories. So the virtual observatory is an international research data infrastructure in astronomy and astrophysics. The IVOA, which is International Virtual Observatory Alliance, was formed in June 2002, and presently there are 19 VO projects from Argentina, Armenia, Australia, Brazil, Canada, China, Europe, France, Germany, Hungary, India, Italy, Japan, Korea, Russia, Spain, Ukraine, the United Kingdoms, and the United States. The mission of this IVOA is to facilitate the international coordination and collaboration necessary for development and deployment of the tools, systems, and organizational structures necessary to enable the international utilization of astronomical archives as an integrated and interoperating virtual observatories. The virtual observatory is an international research data infrastructure in astronomy and astrophysics. VO defines standards for finding, accessing, using, and describing data, ranging from catalogs to images to complex datasets. Virtual Observatory brings together about 50 data centers worldwide adhering to these standards, which include many major players like the CDS, NASA, ESA, CADAC, and many others. Virtual Observatories joins the efforts of the authors of client software, libraries, educational material, web portals, scientific platforms, and creates a platform for all to cooperate and make data intensive research in astronomy possible. IBOA organizational chart is given in this chart here. We have executive committee with the media group, committee on science priorities. Then under the executive committee is the technical coordination group and standards and protocols committee, which defines the protocols and standards in which data has to be acquired, clean, distributed, and so on, to make it available to the whole community, and setting standards, making it possible for people to utilize this, access this data easily, and to utilize it to make science cases. So make working groups, work on applications, data layer, and access of data, data access layers, data models, semantics, registry, grid and web services. And the interested groups work in education, theory, data curation, time domain studies, operations, discovery of new knowledge, and solar systems. So the type of data which we have in astronomy, we may have images, we have spectra, we have catalogs, and polarization, and even simulations data. The images data comes in as two-dimensional arrays in different wavebands, and which helps us create colored images. So CCD images which we get are, as you all know, black and white, but getting data through one or two or more filters, we can reconstruct the images of these data. And the images can be point sources for star-like, quasar-like objects, or extended sources for galaxies, nebulae, and so on. It has been decided that the images, that astronomy data uses the FITS format. FITS stands for Flexible Image Transport System, in an open standard defining a digital file format useful for storage, transmission, and processing of data. Formatted as a multi-dimensional array, for example, 2D images or tables. So a FITS file would not just contain an image in it, but in one band, but it could have different slices of images in different wavebands. Then it also comes with information regarding the details about the image, about the exposure time, about the temperature of the CCD, the time, the duration of the exposure, and various things which are very important in analyzing the data. So as we go through the tutorials, you will get a handle of what these FITS files are and how to handle them. So FITS was designed specifically for astronomy data. And it doesn't just carry images, but it can also carry photometric and spatial calibration information, including the image metadata. So it comes as FITS cubes and so on. Then we have one-dimensional data, which is the spectra, the type series data. And we have these data cubes where data is stored in three-dimensional cubes, each slice having something which I have, and FITS very beautifully handles this. Then we have these catalogs of which are multi-column tables where you have, say, the name of the object. Then it has, you may have the positions, right ascension, declination, galactic longitude, latitudes, and various things. Proper motion array, proper motion deck, and metallicity, and parallax, and various things. So you have these catalogs, very large catalogs. Then we have the science time series data of objects. And what are the tools? The three main users of virtual observatory tools and services is one, browsing images, not just looking at images, but accessing them and analyzing them. Then the second important thing is searching for catalogs. And third thing is find available data for a specific object. And this is got from, for example, image visualization is done through Aladdin, DS9, etc. The catalogs can be accessed through Simbad, Vizier, Topcat. And as we go through the tutorials, you'll see what these things are beyond just having names attached to this. And since we are dealing with tremendous amount of data, it has become very important to use programming languages to analyze this. And gradually, in present times, Python is the forerunner, and this is becoming very important. So we'll be having some hands-on sessions with Python too. We have AstroPy, which is a very good set of modules to analyze and handle astronomical data. It's very important that we do not use them as black boxes. I have given a link right below. The beauty of virtual observatories and services and the tools that they provide is there's a lot of information available on the net. They are easily downloadable. They are freely downloadable. And there are tutorials available on the net. And you can go to the links which we are going to provide to access those tools, download them. You can use these tools to analyze not just the data from the internet, but also data if you have it on your systems. So we have the metadata which describes information about the data. We describes the image telescope exposure time and various things, and simulation and spectral show. So here, a short thing on how to access data. We have CDS, the Strasbourg Astronomical Data Center. It collects and distributes astronomical data catalogs related to observations of stars and galaxies and other galactic and extragalactic objects, solar system bodies, and even atomic data. We have Simbad Astronomical Database, which has, as on 7/10/2025, there are 20 million, more than 20 million objects, 20,175,597 objects, and it has 69 million identifiers and 453,000 bibliographic references and the citation and various things. If you look at the box below in the same slide, you will see that just 4 years from now, in 2021 December, it had 20 million, and today it has grown to 12 million. Now it's gone to 20. So the amount of data flowing in is tremendous, and hence requirement of these VO tools. We have Vizier services, which is a query service for catalogs and bibliographies. So cross-matching catalogs, NED objects, Simbad's objects can be accessed through queries using the Vizier services. It provides the most complete library of published astronomical catalogs, tables, and associated data with verified and enriched data accessible via multiple interfaces. You can get them either through the query from their uh, web pages, or you can query them through Python Jupyter notebooks or through Python code. And so there are various ways you can access this thing. These query tools allow the user to select the relevant data tables and to extract the formatted record matching given a criteria. I can specify exactly what columns to download. You can specify, say, in terms of the right ascension declination on in terms of luminosities or parallax. So you can choose your criteria and download from the databases. We have Aladdin, which is again a very beautiful tool. It is an interactive software sky atlas, which allows users to visualize digitized astronomical images and superimpose these images taken in different wave bands and different catalogs and databases. So we'll be having hands-on sessions. We'll run you through some essentials of this thing. So apart from this, as tools for astronomers, which you can find in public domain, are VO tools. Yeah, so we have VO table, which is to display and analyze the tables. VO plot, VO TopCat, Mirage. These are for plotting and accessing data from catalogs. We have image display and tools like Aladdin, which I've just mentioned, DS9, Skyview, OSs. For spectrum display and analysis, we have VOSpec, SpecView. And R and Python are two public domain open source softwares which are can be extensively used for statistical analysis of these vast amounts of data. Apart from this, there's a list of proprietary and public domain and open source data which people can use. But VO tools themselves are very powerful, which one should get used to handle this data. So the last word from me is virtual observatory has matured. It has made availability, accessibility of data very simple, and the tools which they provide are very easy to use and very powerful ones. And virtual observatory promises us a new and exciting era in astrophysics. Thank you.
Yeah. Thanks, Najam. We'd be happy to take some questions. If we have some questions from the audience, please post it, or in the afternoon session, that is post-lunch, we will take you a walk through each of these websites. For example, the CBS Strasbourg, as well as Vizier, etc., to actually show how these things are done, right? So in the afternoon, we'll be actually installing some of these tools, etc. But meanwhile, if there are any questions, I would welcome people to ask questions. You could unmute yourself or write it in the chat window. To exit your stop share. Yeah, are there any questions? Yeah? Okay, fine. So we'll continue, no problem. You're welcome to continue writing your questions over here or on YouTube. I'm also monitoring YouTube, and yeah, there's nothing over there too. But you can post your questions whenever you wish. Right. Proceed? Yeah. So we'll continue now with this thing. So at present, we have 3 talks which are half an hour each. Najam spoke to you about VO. I will be talking to you about AI, and then Shanshan will talk to you about AI VO in China. After that, we will, so this is just a brief warm up for everybody to tell you about what we are going to talk about. And then after that, we will be having sessions where we will actually hands-on give you, an experience of using these VO tools, etc., that we are talking about, right? So first, we just have these introductory 3 talks, and after which we will, this thing. Yeah, so there's a question by Kamal Raj. Are all the packages open source and accessible? Yes, they are. If you're using Python for all your stuff, and all VO is also all open source and accessible. Instead, most of the VO stuff is developed on Java. So it does not make a difference what is your operating system, whether you're using Windows or a Mac or a Linux machine, whatever it is, it's fine because most of it is Java based. So you'd be accessing it through your browser, and these things will. Yeah, so Adip has been asking, will all the sessions be introductory or familiarity is assumed? So we'll actually go along with the flow, right? What do you say? It depends upon the level of the participants. We can check with them because in principle we have like more than 400 registered, so we are not very sure about this thing, but we can move you all at all levels. You can talk.
Yeah, so we'll see the audience as the requirement. The first three talks which we are having now were introductory as to what is VO and how AI is important in astronomy, which we will be talking about. But if the audience, the people, participants require something more specific in detail, we can do that. So, yeah.
Yeah. So if you, Adeep, if you do have some specific requests, you're most welcome to write it in the chat window, right? And we'll try to address that too. Yeah. Okay. So we'll move on to the next talk, which is the one about AI, and right. So I'll go on to start. Okay. So yeah, so we'll talk about AI, machine learning, etc. in astronomy. Like I mentioned in the previous talk, I will even take you all a walk through scikit-learn. That is the Python package which is generally used for machine learning. It's the most comfortable package to use for machine learning. So in case you want to do machine learning, that is the best way to go about. And yes, all of it is open source and very easy to use. So that should not be a problem at all for anybody. Okay. There's another question also by Argadeep Biswas. What are the main attributes that must be collected while collecting data of stars or galaxies? It just depends upon what are you looking for, right? If you're looking for data of stars or galaxies, it could be photometric information, that means brightness in different filters. It could be spectroscopic information. It could be anything. So Argadeep, the whole thing depends upon what is the science case. What are you trying to study? And that will define what is the data you want. Do you want time series data? Do you want to see how the brightness of a particular star is changing with time, etc.? So it all depends upon what is your science case. What is it that you want to study? And depending on that, you need to decide what is it that you want. Because there's a whole world of data and opportunities available. You have to, based on your science case, decide what you need, right? Okay. So I think there are no more questions. No? Yeah. Okay. So let me proceed, and I'll go ahead. Okay. So this is as a mandatory this thing that AI is. Most of you all have heard about Alan Turing, who's considered the father of modern computer science. There are various people, John McCarthy, and many more who've actually contributed to this whole experience of artificial intelligence and how it has been developed. The basic concept being is you want a machine to learn from experience, not just behave, just do what you tell it to do, but also to learn from experience, which is actually what we human beings do. When we talk about intelligence, often we are referring to the expertise we gain because of experience, right? So, yeah. So first of all, I'd like to clear these three concepts. One is artificial intelligence, machine learning, and deep learning. Because in today's time, you see that all these things are being referred to, and people are not too clear about what's the difference between all of them. So let's first clarify, right? So what is artificial intelligence? Artificial intelligence is a broader thing, okay? It's the broadest thing rather. It's basically the simulation of human intelligence processes, okay, by machines, specifically computer systems. And the specific applications of AI, they could be expert systems, they could be used for various things, even natural language processing, speech recognition, machine learning, various. So basically it is generalized learning, there's reasoning, problem solving, all that bit which is part of artificial intelligence. So artificial intelligence in principle is the broader thing, right? The other thing which we then study is what is called machine learning. Machine learning is basically about teaching computers to learn and improve from data, right, without being explicitly programmed for every task. I'll explain to you what does that actually mean. It basically, it's a subset of artificial intelligence where systems learn from data and they use it to actually improve their performance on a task without being explicitly programmed. The same thing, but I will try to show it to you through examples as to how is this actually done. And then there is deep learning. What is deep learning? Deep learning is actually a branch of machine learning, right? So actually the largest set is artificial intelligence. A subset of that is machine learning, and within that a subset is what is called deep learning. Now deep learning is the type of machine learning. It actually uses what are called artificial neural networks, okay, which has multiple layers to learn from large amounts of data. So you have your input, you have your output, and you use that to determine hidden layers, okay. And in that way what happens is it actually, with these neural networks which it builds up, it actually excels at tasks like, for example, image and speech recognition, language translation, which now we are using so much, right? So most of the language translation applications which we are using, Google Translate, etc., they are all using deep learning. And for example, self-driven cars also automatically identifying and learning patterns from unstructured data, etc. This is what we call deep learning, right? So like I mentioned, what came in the beginning in the 1950s till the 1970s, 80s was artificial intelligence, was a way of, getting machines to do things. Then you have machine learning, where you concentrate on machines, where they excel at their task. And then deep learning is this thing. And we'll actually take up specific examples, which hopefully will make it more clear as to what each of them are, right? So so basically with deep learning, what you do is you can see data and patterns. With machine learning, you can predict things, and all of them are part of artificial intelligence. And then there's the other thing which nowadays you are seeing very often, which is generative AI, right? So generative AI is what we are using, ChatGPTs, DeepSeek, Suta, various things. This is basically, it is an artificial intelligence which is capable of generating text, images, other data to generative models. And these are various, we are already using many of them. They could be used, applications are there in art and design. It could be composing music, it could be creating content, it could be fashion product designing, it could be translations, or all of the things that we are using, right, in today's time. These are all what we call generative AI, right? And it's very important to understand these things and the structure of them, because finally, you're using these tools, and it's good to know what these tools actually mean when we are using them. Right. So what are the tasks that we use this AI for? Various things. For example, on the upper left, you see this image of a street, and you could be using it for object detection. For example, maybe you need to read the boards or something like that. It could be for natural language processing, which is being used a lot like now. You have our large language models, etc., which are being used in ChatGPT, in DeepSeek, etc. You could be also using it for things like expert systems, as well as robotics and various applications like that, right? So artificial intelligence, or what we call strong AI, it actually involves machine to possess the ability to perform an intelligent task like a human being can, right? So essentially it has been made to make our job easier. Only problem is, there was a nice thing which I should have probably put over here. It's like crazy that in today's times we are using AI more to do all the more smart things, or the more artistic things we would like to do, like, write poetry or compose music or do paintings. AI seems to be doing an excellent job of that, while, the mundane ones are still left for us to do. So in short, there are many applications. For example, in healthcare, in healthcare organizations, you would use it, for example, for medical diagnostics. You have certain symptoms, you use symptoms to actually infer what is the thing, and then various other processes, because you characterize your patient, etc., certain properties, etc. Google Maps is something which we constantly use all the time, and it tries to look for shorter paths, faster paths, based on the changing data of the structure of the road and the traffic, etc. And I'm sure people who are using Google Maps, you can see the pros and cons on it. So it's not that it's actually achieved what it should finally do, but it is getting there, right? It's getting better with time, and it will hopefully, with time, it should get even better. Okay. I can see there are some questions on the chat window, but I will take them towards in the end. First, let me just finish this business and then I'll get on to it. So for example, there's a Google Eye Doctor which can actually examine retina scans. Similarly, they are also using AI a lot, for example, not just for retina scans, but you could have various diagnostic tests of people, and the number of experts are limited, right? For example, if you have to inspect CT scans or MRIs or things like that, you can actually use AI to scan it before you actually address an expert to look at it. You may still use AI to actually check on it and see how good or bad it is, or what are the things about the data, right? Facebook, all of us use Facebook. You can clearly feel it, sense it, that there's somebody like Big Brother is looking at you. You can actually see how machine learning, deep learning is actually, this is the example of how it uses facial features to tag your friends. If you check it out with a picture of your friends, it actually quite well identifies and tags your friends, but it also tags you and identifies your choices, etc., to decide what are the kind of things it should advertise for you, etc. Twitter, etc. I won't go more into this. Let me jump. There's Tesla also, which does it. But let us focus a little bit on, we've spoken a bit of machine learning, but let us now go back to astronomy. So in astronomy, like you heard in the previous talk, you have the virtual observatory, and that's basically because there's a very large amount of data, right? And therefore, what happens is you need some artificial intelligence to actually sift through your data and inspect it and analyze it, so that it can be then done in numbers which human beings can handle, right? Otherwise, the number of, if you're looking at Gaia data, for example, it's 1 billion stars in our galaxy, right? So it's obviously impossible for somebody to look at data of 1 billion stars and look for patterns in the data, right? What we basically want is we want to look for characteristics, for patterns in the data. And for example, I myself work with star clusters. Star clusters are groups of stars which are born from the same molecular cloud. And because of that, they lie in the same region of the sky. And because they are born from the same molecular cloud, they would obviously have, the position is there, they are close to each other. But other than that, even their velocities would be similar, their distances would be similar, their chemical compositions would be similar, right? And the age of the stars is going to be similar. The only difference would be in their masses. So what happens is, if I'm looking at 1 billion stars and I want to look at all these characteristics of these stars to identify clusters in space, I need to look at like some 6-parameter space for which I can actually look for clustering and identify clusters. And therefore, I obviously need some kind of machine learning, some kind of, help in that sense to actually sift through that data. So what we actually do is the types of machine learning. There are basically 3 types. One is what is called supervised, there's unsupervised, and there's reinforcement, right? So supervised learning is, for example, if you have some labeled data, right? For example, if you see in this case, I can show you I have labeled data. Supposing I have 3 images of a lion and 1 of a frog. I say that these 3 are a lion and this is a frog. In my case, what I've done is slightly bad because all my 3 images of the lion is exactly the same. But in a realistic case, what you can actually do is you can take an image of a lion from 3 different angles, for example, and use that to train your system that this is what a lion looks like, from 3 different angles. This one is the same image, so actually this is bad. I should change this. It should be from different angles and different sizes and shapes. And then when I present my system with an unknown object, the system should identify and say whether that is a lion or not, right? So this is what we call supervised learning. That means you already have some label data, you know what it is, and then you give the system something like some unknown image and you ask it to categorize that image, okay? Now, the advantage in supervised machine learning is that you can do what is called validation, right? One of the biggest problems of machine learning is that since it's a new tool which people are using, not everybody trusts it, right? And therefore, what happens is if I say I use machine learning for a certain purpose, I need to validate what my results are. So in supervised techniques, the standard method is you divide your data into 70-30. So for example, I use 70% of my data to train right? So for example, I had 100 images of lions. I only used 70 of them to train my machine that this is what a lion looks like. And then the remaining 30, when I do it with unknown images, I also insert my 30 images, right? For which I know whether it's a lion or not. And then I see whether how well does my system identify it as a lion or no. And then, for example, I discover that, okay, my system does 80% correct or 90% correct. So in that way, I can validate my data. I can actually see how well does my algorithm work, right? So that is something very, very useful in supervised this thing. Only problem in that is that then your labels, you have to be very confident about your labels. Your labels cannot afford to be wrong, because if your labels are wrong, then that will confuse the system, right? Your results will be bad. The other technique which is used is what is called unsupervised learning. In that case, you do not know, you don't have any label data, you're not making any assumptions, but you look for patterns. So that's the kind of data which, the kind of analysis I have been doing with star clusters. When you're looking at stars which are of, with the same distance, at the same velocities, and maybe same chemical compositions. So we look for clustering in that n-dimensional space, which is made up of distance, velocities, chemical composition, various other factors. And I look for clustering of that kind, and then I can identify clusters, right? So that is what is called the unsupervised technique. The other one is the reinforcement technique, where it's a combination of the two, and you use that to kind of learn from your mistakes. So here I have that example of supervised. So similarly over here, you can actually use supervised techniques to actually look for similar data, right? So here is the image for supervise this thing. You have label data, you train your model, you predict it, and you actually say whether what kind of data you're looking at. Now, how do we use this in massive astronomical data sets, right? So what happens is we actually choose the appropriate statistical task, okay? And we use the fastest algorithm data structure for the statistical method. I'll show you what do we do. The basic difference in this is that in today's time, see, in earlier times, when physicists or astronomers, they worked, they basically did what was called hypothesis-driven science. For example, I had something happening. I do an experiment with electricity, etc. I do it with the star. I'm looking at the sun. I'm seeing how is the sun evolving, what is it radiating, etc. Right? I look at one star and I use that to build up a hypothesis about the star. Right? Then I do some experiment. Right? So I do observations of the sun. I actually observe sunspots. I check the magnetic field. I do various things. I do some data analysis and I build up some understanding of what I think is the sun and what's happening on the sun, right? But that was the times when we didn't have that much of data and that much of this thing. Now in astronomy, experiments are observations, right? And now the thing is that with present days, we do have so much of data. So now the kind of science we need to do is slightly different, right? It's quite different rather. It is basically what we call data-driven science. You have loads of data sets, right? So I'm looking at a billion stars, say from Gaia data. So when I look at my billion stars, I can now look for patterns. What are the kind of brightness of the stars, or at what distances I can convert it to absolute magnitudes. I can see what is the brightness of stars, what is their typical, their chemical compositions, their various factors, and I use that to actually build my theory. So I use the data to actually build my theory and do analysis and improve my understanding, right? So now it is a data-driven science where you need to do Yeah. So one is what is called classification, one is what is called regression. So classification means, for example, like the dog-cat problem, right? So either an object is a dog or it's a cat, so you classify it, right, in one of the two types, and that is your classification, right? The other method is what is called regression. Regression is when you're using it to, say you're doing a straight line fit, right? So you do a straight line fit to predict continuous values. So you have some data points and you can use it to actually do prediction by fitting it to something, right? So based on that, you could use it for both these tasks, classification as well as regression. So let's take an example. If you're looking at galaxy images, right? So if you we don't do, there is a citizen science project called galaxyzoo.org. Okay. Now, if you look at galaxies, you obviously know they vary in their sizes and shapes, right? There are spiral galaxies, elliptical galaxies, bar galaxies, all kinds of galaxies, right? So it's called the Galaxy Zoo. It's one of the earliest citizen science projects. Now, the thing is that now we have images of billions of galaxies, right? And therefore, the problem is that if every astronomer is going to sit down and classify each galaxy image, we don't have that many astronomers to do that, right? So the idea was, let's put this out to citizen scientists and let them classify galaxies, right? So you train a citizen scientist. A citizen scientist is somebody who doesn't know any astronomy, but who wants to work in astronomy. So you show them images of spiral galaxies and you say, oh, this is what a spiral galaxy looks like. This is what an elliptical galaxy looks like, right? A blob like that. This is a galaxy with a bar. You show them different things and you train them. And then when you train them, they themselves sit and classify a bunch of galaxies. Maybe each individual classifies 2,000, 5,000 galaxies. So in Galaxy Zoo, if you actually participate in this project, you actually get certificates depending upon the number of galaxies you classify, right? So now the same, obviously there are going to be human errors in the classification because you're using non-trained people, right? You're using citizen scientists to actually classify. So what the zoo universe does is the same galaxy is getting classified by 10 different people, right? So you actually look for, either in some of the cases you look for the ones which everybody is classified the same way, or you say take 90% or 80% say has classified this galaxy as a spiral galaxy. So then I say, okay, 90% I put it as classification as spiral, I will put it as that. So more than 90% have called it a spiral galaxy because I know that there can be errors in the classification. So what the Galaxy Zoo project did is they did an excellent job. They did this to actually build up labels for galaxy morphologies, right? Which were actually done by citizen scientists, okay? So they helped them build up the labels for galaxies, which were then used to train data sets that this is what spirals look like, this is what ellipticals look like, this is what bar looks like, various types of galaxies. And then it was actually run to actually classify galaxies, right? So this can be done in that case to classify various things. It could be images in real time, in daily life things. It could be to classify images of people, of not just galaxies, even in astronomy for various images, but you could be using it for similar cases. So what happens is a lot of the software, etc., which can be used will actually overlap. The other important thing in which machine learning is used is the application of variable stars. So variable star is a star which basically changes in its brightness. So this is called the light curve. This is the light curve, the change in brightness of a star. But if you look at these things, every kind of variable stars has a different kind of light curve. So the template for the light curve of, for example, an RR Lyrae star, this is an RR Lyrae star, is very different from the template. This is what is called contact binaries, eclipsing binaries. You look at these are eclipsing binaries. This is their template, okay? This is their signature light curve. Cepheids go in this way, right? RR Lyraes go in this way. Mira variables go in a different way, long period. So all these are templates. So if you have a template, you get from catalogs light curves for say 100 Cepheid variables. So you know what the template looks like. And then if you are actually looking at various variable stars, you can actually match it to the template to actually see whether it gives you what it fits into which. You've got to classify it whether it's a Cepheid variable or an RR Lyrae or eclipsing variable, because you already have the templates of what should the light curve look like, right? Typically, Kepler data basically looks for exoplanets. So this is what we call transit light curve, which is actually quite similar to an eclipsing binary curve. This curve, the eclipsing binary kind of curve. So in Kepler data, you actually use it, and you find the transit. The planet comes in front of the star. The brightness dips, and that's how you're going to actually identify your your exoplanets. So Kepler actually gives you data for that whole part of the sky. Now in that there can be various kind of variable stars. You can use machine learning to identify which of those are exoplanets, for example. So the whole variable star community uses Kepler test data to get light curves for various variable stars. Could be used also for redshift analysis. For example, we know that we have various galaxies. You can see there are various galaxies at different speeds at different distances. And what you can see is that if you plot them, you can actually get that to get what is the Hubble's law. You have the speed and you have the distance. So here what you see on the upper right is the spectrum. So basically the velocities are derived from what is called the redshift. The redshift is the shift in the wavelength of a certain line because of the velocity of the source, which is our Doppler shift or redshift. So because this object is at zero redshift, you can see that there is no, I mean, it doesn't get shifted. But for example, if you have redshift 0.4, then you have this object which is actually moved that much. 0.8 has even moved further. So this is all moved towards the redder wavelength. So you started off with redshift 0. Here's your redshift 4 object. Here's your redshift 8 object. So what you can do is you can actually use it to derive the redshifts of objects in this thing. The three-body problem, which is a classic problem, which actually describes that the system becomes chaotic and highly unpredictable. It has no analytical solution, and its equations can be only solved numerically through a computer. So in this case, what happened is the three-body problem was actually solved using machine learning techniques, where you can actually predict the positions, right? Okay. Most of you all have seen this, the Event Horizon Telescope, imaging of black holes. So what they basically used were what are called convolution neural networks. These are deep learning algorithms. And what they did is basically, because when you took images, if you remember the Event Horizon Telescope, you had data from telescopes all over the globe, right? And you are trying to look at a very high resolution image of the image of a black hole, right? And therefore what happens is the image had to be actually reconstructed. You don't have all the points on the image, okay? And the reconstruction was basically done using convolution neural networks, and that's how they actually built the image. So machine learning methods are actually gaining popularity. There's further exploration of their methods and their potential. Only the problem is, the deal is about what are the algorithms you actually use depending upon your science case. So finally, in the whole story, the whole most important question which you are going to deal with is, what is your science case? Okay, what is it that you are actually trying to study? Okay, and based on that, you will define what is the data that you're going to deal with, as well as what are the algorithms, machine learning algorithms. We will show you the scikit-learn page, etc. later on, and we'll show you the different algorithms which are available. You could be using convolution neural networks or clustering algorithms or random forest supervised techniques. So it depends upon the science case you have and the kind of data. You need to know the kind of data you have, and how does your, what is the limits of your problem and what you can achieve, right? So one of the most important things about machine learning is you need to know very well what are you using it for, and what is it that is actually giving you. Whatever you use, you know whether it is, what you actually want or no. And I don't have the time, but I kind of briefly told you how I'd actually used it for star clusters. But you can actually, that is my area, that's what I work in. But in principle, you can use it for a host of different purposes, machine learning. And like I said, the important thing is, what is your science case and what are you working it for? So I can see already there's a question on the chat, which is by Sri Lakshmi Radhendran. She's doing her master's in communication and signal processing, astronomy data for MTech project. In principle, you can use it for signal processing, but and you can contact me. But digital signal processing, it's better if you do it with radio astronomy. So if you find somebody in radio, that would be far better, I would say. And but you can get in touch with me. I'll get you in touch with people. Ankit Yadav is asking when machine learning actually useful for model fitting. Okay, yeah. So like I said, model fitting, for example, like variable stars, when you have templates of variable stars, you can actually use it to identify the different kind of variable stars, etc. And yeah, so Ankit, the question you asked is that how can we determine whether a particular astrophysical model or problem would benefit from using machine learning rather than traditional fitting approaches such as Bayesian analysis or grid search or to this thing? So my answer to that question is we really do not know. So what you actually need to do is you need to try it out you have to try it out in this way as well as that way, because there is no hard and fast answer to that question, according to me. Maybe Shanshan can also answer that, but I mean, the others can also answer it. But I would say that there's no hard and fast rule. What I would actually advise is you try it out. Try this, try that, and you then probably this thing. We'll have to move on, and I'd now hand over the deal to Shanshan, and she's going to talk to about AI and BO in China.
Yeah. Hi, can you hear me? Yeah. I think for that question is like sometimes we use machine learning and this techniques, and it's maybe faster and to get more the speaker.
Can you
Let me, yeah.
the sound of the sound of
Okay.
sorry, remove the sound of your computer, please. Quita el sonido de tu computador. It's the sound of your computer. Sound issue. Yeah.
I will go ahead share my
Okay.
PowerPoint.
Yeah. Sorry. Only one of those Apple things to your things.
Okay. So everyone, I think I'm okay to go on, and I think this session will be the last session about it's introductory session, and I will tell something about the China VO, which is the China Virtual Observatory, what we are doing this years and what we have done this recent years to try to use.
They're not present.
Oh, no.
This is what we're saying.
It's okay. I will share. Yeah, maybe. I will share here. It's really strange. The whole screen. Yeah. This is better.
Yeah.
Okay, so China VO and AI developed in China. And just to give you some ideas what virtual observatories technologies and protocol standards can be used in astronomy by scientists and telescope to precise telescope data and this kind of things. And what we are doing in China is now building a national astronomical data center and try to manage the whole life cycle of astronomical data using the virtual observatory technologies and to provide some resources and services. I will talk later. So is the PowerPoint showing? Oh, it's out.
Yeah, it's showing. It's all fine.
Really strange, but I
We can see it, Shanshan. I can see it. I can see it.
I should go to this one. Yeah.
Try to move it just so that make sure that.
Yeah.
Yeah.
Okay. Okay. So I think Hansen has mentioned this before, that modern astronomy is more data-driven scientific discovery. So before 2000 years, it's the era of terabits. And so we have the Sloan Digital Sky Survey, the LAMOST, which is a telescope in China, doing the observing the in the optical the spectral and in the era of right now, I think we are at the era of petabytes, and there observatories like the FAST in China, which is also in China, and the Gaia Space Observatories and the Pan-STARRS, which are all famous observatory and surveys, and they produce data in petabytes. But future some projects like SKA, LSST, Rubin, and they have already started to release data, and their data is huge. And also the China Space Station Telescope, which I think will launch maybe in 2 or 3 years, CSST, is also going to produce huge amount of data. So we have to deal with this data, and like this big data, this book site that astronomy is the origin of information explosion itself. And so we have to deal with all these informations. So that's why the virtual observatory is come out, and scientists and engineers try to use the technologies to achieve the goal, to precise astronomical data and make it available to all the scientists else around the world, and can use this can use the virtual observatory technology to study, to access the data, to publish the data, and all these kind of things to work seamlessly together. So there I put a sentence like from Chen Zhoucui. He is the leading scientist of our China VO project. He said that data-intensive online astronomical research and application environment is the virtual observatory. So taking advantage of advanced information technologies to achieve global access to astronomical information. So this has also mentioned by Hansen before, and so at the origin, the IVOA, the Virtual Observatory Alliance, has 19 members, but right now it currently have 23 member VO projects around the world, and we have 6 working groups and 8 interested groups, and 46 interoperability standards. Yeah. So there were the IVOA held 2 interoperability meetings per year, and one is in May and the other is in October or December every year with the ADAS meeting. So this year, so the meeting will held in Germany. I think it's in the November. So this this event is completely open for all people around the world who are interested in virtual observatories alliance to join, and you can log into the website and browse and see if you are interested in and to participate. I think so. Quickly review of the what IVOA, and I will talk about the China VO. The Chinese Virtual Observatory is the national VO project in China, initiated in 2002 by Chinese astronomical community, leading by NAO's the National Astronomical Observatories. So under the guidance of the experts, including Dr. Jim Bray, Alex Sally, and Professor like George, China VO has been a very active member of the IVOA for over 20 years. We have built like the China VO platform, the unified access to online astronomical resources and services, and the VO ready projects and facilities. And we have do a lot of public education activities in China and sometimes around the world. So based on 20 years work of the China VO and the astronomical informatics work, so we built the NADC. It's the National Astronomical Data Center, was formally announced by Chinese government in June 2019. It's a huge thing for us because we have officially recognized by the government, and we have some fundings and to do what we're trying to do for a long year times. And it's also a signal that government is taking data seriously, and they notice the importance of the astronomical data, and they're trying to help us to build this data center. So for China VO, we have an official website in Chinese and in English. The English version is a little much simpler, but in Chinese version, we have a lot of channels and a lot of projects. We announce news pretty every day. So we have some meetings, we have some new discoveries that scientists use the VO data to produce, to do their research. So we try to publish their achievement. So these channels, including like observation, the data discovery and exercise and the cloud computing, we built a cloud computing platform, and the scientist platform. This is a newly thing we are building right now, and we have started the trial. The public channel, including citizen science that Priya has mentioned before, there is a Galaxy Zoo in the world, but we have our own citizen science platform in China. We have like 6 projects right now. So yeah. So the astronomical data center, this is the structure, some structure of the VO, but I want to see that we are providing the whole life cycle management of the astronomical data, from the observation to the discovery, to the science discoveries. So I will give an example of how we're doing this. Use the LAMOST spectroscopic survey, which LAMOST is one of the biggest telescope in China, and its first phase started as 2011, but it's now getting into the 3rd phase, and each phase you can see is the 5 years phase, and they are producing a lot of spectroscopic data. And the data is divided low resolution and the medium resolution, and will release every year, and sometimes every season. So it's a complicated thing to do this data release releasement. So this is a illustration of the observation and data processing. And this is the interface that we are building for we build for the LAMOST. And you can see that it's getting the data released 13 years, and each data release have different versions. And we also have some international collaboration, so we make sure that LAMOST data is not only used in China. We use the VO technologies to try to get this data around the world, so people around the world can use this data to do their research. So this is the low resolution size web form. You can acquire the data, and the output format, the data is can be downloaded as the CSV, the JSON, the VO table, and the web page. So here is a web form search output. You can see for each spectroscopic, and there is a phase file, the PNG, the CDS portal, all these informations in line. And if you click, you can go directly to CDS website and to see their these details. But also you can just select the data you are interested in and to package them, to download them to your computers. So if you don't want to download, you just want to check if this is the data you want, you can use the online platform to see this like visual illustration, and to analyze the spectroscopy. So this is an example of the medium spectrum viewer. So you can see all because the LAMOST observed one target several times in one night. So you can see different spectra in one figure. And here is the example of the URL list for bulk download. So you can download whatever you want and to use the service we provide. So to use the VO services, we also provide some simple colon search, the simple spectral exercise, the TAP, all these services. So if you are familiar with the VO services, VO protocols, you can access the LAMOST data very easily and to do your research. So also, if you are familiar with the TopCat, I think we will introduce the TopCat later in this training. So you can get the VO data, get the LAMOST data through the TopCat and do the colon search. So we also provide a package called PyLAMOST. So if you download, just go to the GitHub and download this PyLAMOST, you can easily access the LAMOST data, use UPython code. So yeah, this is also a service we provide. And the data access at LAMOST database. So this is all the conclusion, what we are doing. You can see there's a lot of things going on. And thanks to all this works on our team, the LAMOST data used around the world is a kind of explosion recent years. And there's a lot of, before this, only Chinese scientists use LAMOST data to do the research. But right now there's more and more scientists around the world using LAMOST data to do their science project. And so what I just give is an example of how we use the to support a project, a telescope's data release in China. And right now, we actually not doing only LAMOS, so we are supporting Einstein probe, which is a telescope observing transit. Yeah, but they haven't released any data to public right now, but it will come soon. So at that, I think maybe next year, yeah, they will have their first data release. So the NEDC resources and services is including data storage and data access. You can see all this list going on is all focused on the astronomical data. And we are trying to use all these platforms and technologies to maximum the potential of astronomical data, not only in science area, but also in the public areas and to support AI training, like Priya mentioned before, to try to make astronomical data to AI-ready data. We are currently doing right now, because you have to remodify the data in some way so they can be used by AI training. So far we have like total volume of 83 petabytes data in our data center. Most of them are local, the Chinese of the astronomical data, and some of them are mirrored data sites. And all this data project and have supported many science discovery and papers. So I will give the last thing I want to talk about, the AI ready data, the AI astronomy AI projects we are doing in China right now. So the collection of this is a list of the collection of AI application data sets for astronomy. Currently, we are trying to do in China, and we are trying to modify like DASI data and Gaia data, try to make them labeled and can be used in machine learning and the large LLM training and this kind of things. So I'm sorry, this is also the AI service. And for these things, this machine learning, these trainings, they can the scientists can do these things offline on their computer, but sometimes if you want to work with huge data, you have to do this online. So we build a science platform, and the HPC based on the cloud stack and the Slurm, and we set up the cloud computing environment for astronomical data processing. In this environment, each user has private space, which can be shared among different virtual machines and the desktop systems. So you can see we have pre-installed many astronomical data process softwares like the TopCat, the DS9, all these kind of things. And we also have Jupyter Live and VS Code, so you can code on this platform to do your machine learning on these platforms. So this is another AI thing we are doing in China right now. It's called AI large model platform. you can see on this platform, we currently have 6 AI models. Some of them is the universal astronomical large LLM, like Astro One. So you can ask like you chat with the ChatGPT, you can chat with the Astro One and to ask all the questions about astronomy. There are other models like Jinwu and like Falco. They are dealing with some very narrow area in astronomy. Like Jinwu is it's a model focused on sign. So it can, if you upload a picture of the sign, it will tell you what's going on these pictures. Yeah, is there a flare or is there like yeah, all these activities going on. And so one thing, the last one, the NADC agent is what we are trying to build right now. We put in a lot of effort here. You can see this agent is the leveraging the NADC's rich data and software services and the reasoning planning power of large models. We build AI agent that deliver intelligent time domain alert analysis, coordinated observation planning, and multi-source data fusion, deriving the integrated ground-space time domain astronomical discovery. So there's a demo on the screen. You can see how the scientists can talk to this agent, and the data is giving back. For now, this data, all this data and this information is coming from the EP, the Einstein probe, the observations. You can see all these things, and it's currently used by the EP team, and they use this as an advisor, so they can plan what to observe and to arrange the planning, the observation planning. So, but future, we hope this can be public and be used by more scientists. So we also have built some MCP server based on open APIs. So this is an example of the MCP we built for the Lamos data services. But we're also building the EP services. So this kind of the two task scope we are focusing on, but soon we will trying to build more, and we're trying to put our NADC services all to maybe MCP, so the others LLM can use our services around the world. Yeah, hope so. The last but not the least, here is the China Vivo Citizen Science platform. And these are all the projects we are providing in China right now. You can see the Galaxy Circus, Galaxy Maze. These are 2 projects similar to the Galaxy Zoo. And people can classify if this is elliptic galaxies or spiral galaxies. And there are gravitational lens finder project and supernova, popular supernova project for finding supernovas, and the reporting fireball system, and all this kind of things going on in China. And some of them have English versions, but I think if maybe later, so if people from other countries are interested, we can try to make it a multi-language platform, so you can all participate in. So future version, the last slide, future version and vision. And we try to continuously improve the NADC capabilities to meet every user's need. So integrated ground space data fusion and the governance. Yeah. And so thank you for everyone, and hope.
Thank you so much, Sunshine. Do we have any questions? Please in the chat box. Meanwhile, I've also shared a poll so that you could let us know your levels of Python video so that we can adjust the levels, right? So please fill that Menti poll. And questions for Shanshan. So do we have any questions? Or I think people are running for tea. How many do we have offline, Rafael? Shanshan, there's a question on the chat window. It's a long one by Newton or Dare. Would you like to take it?
Yeah, I have used them in space-wide
Yeah.
activity,
Yeah.
but haven't so far found any error.
I'm coming in your screen.
I'm not sure if I quite understand it right. Do you mean that there is there error quantification implementation for machine learning astronomical data? I have.
Yeah, even I'm not too sure about what's the answer to that question.
I can't hear.
I think that I said there's a question in the chat window. I think you read it, right? This is Newton from University of Nairobi.
I think it's for the machine learning. It's for,
yeah. Oh, okay, it's machine learning. Okay, fine. Yeah, so I would say that I know that ChatGPT, the language models, they do hallucinate, right? I know about hallucination with the language models. I'm not too sure about the other ones. I do not know whether they hallucinate. And but probably, like I mentioned, is that one has to always be careful with machine learning because you can get, I mean, it can give you wrong results. You have to validate.
The scientists I'm working with, they are really careful about the machine learning's result, the LM, and sometimes they refuse this results. And so we are trying to use the agent, the NADC agent, like these technologies, to control for some way to control the result. So we only allow the LM to give information in some very specific things, and we don't want them to give information randomly. Their long answers, we don't want that. We just want them to give very specific things we are interested in. Yeah.
So there's a question for you, Shanshan. Is there a video or manual how to use Lamos data? Can I find spectra of transient objects like novae?
Is there a video or manual? How to use? To find novae, I'm not sure. I personally, my study is to using the Lamos data to find the binaries.
My question is Lamos a survey data style or is it pointed observations?
A survey, it's a survey. So
then it could probably cover novae, right? You could probably look for
It's I don't think you can do it.
I'm going to hijack my own tutorial.
Okay.
And we're going to try to do it.
Okay. Yeah.
Sorry, okay. So we will now be stopping for tea. And yeah, what is Alexandra saying? Because in half an hour he has to take.
Alexandra said he will try to do this later in his
But he has
session.
it after half an hour, right?
After the tea break.
After the tea break. Okay, we will.
Yeah, we're going to try to look at Lamos spectra via TopCat during my session.
Great.
I haven't tried myself, so I'm going to rely on Shenshen.
Okay.
So Alexandro, you have it after half an hour, right? In 30 minutes.
Yeah.
Yeah. Okay. So yeah. So we break for tea, and in 25 minutes we meet with Alessandro. Yeah.
Okay.
In person at the library.
Is everybody back?
Yeah. Okay. Hello, Priya.
For the ones who are in this room, let's just use my my audio. Maybe it's easier. Okay, awesome. You're only seeing, okay. Let me know if I can start. I'm trying to find
Yeah,
my
Alexandra, you can start.
Okay, cool. All right.
Yeah. I'm here. Bye.
Awesome. So let me find my notes. This is going to be easier. Right. Okay. So what we're going to try to do is we're going to try to use some of the VO tools. And the beauty of VO tools is that they allow you to access data which are available on the virtual observatory without having to worry about everything which is going on in the back. So let's start with something easy, and let's start with perhaps one of the easier entry points. So actually, I was giving a presentation about some VO things a month ago, and a colleague was asking, okay, so what is a good entry point for VO? So if I want to start using something, what should I use? And this sounds to me like a good start. So in this example, I'm going to go like, okay, so I vaguely remember that there is an object which exists, and I want to figure out what this object is about. So for this example, I'm going to use the Whirlpool galaxy. You're going to find out why I'm selecting this one. So this is an object that you probably have heard about, probably have seen. Is the 51st object of the Messier catalog, and Simbad has this beautiful thing. Simbad is Hassan has commented it already. It's basically a curated database of astronomical objects. It has millions of objects, and it stores the name of the object, the different types. So you can see, actually, if you hover over.
Sandra, can we have your video?
Sorry?
Can we have your video, please?
Oh. Don't you have it?
I can see your screen.
Can you see my screen and my face? Pardon?
Now we can see it.
Okay.
Thank you. Now
Okay.
it's all. Yeah.
So basically you have the name of the object, you have the type of the object, and you can, this is sort of a conversation that came up during the meeting. When you're dealing with astronomical data, an astronomical object can be several things at the same time. And then you have the coordinates, in this case, in different system, in ICRS, in FK4, in galactic coordinates, you can have the redshift, which in this case, being a galaxy, can be interesting. Sure, this is a galaxy with a redshift of 0.0017, so it's not particularly fun. In the case of these galaxies, you have the morphological type, the size, and most importantly, the photometry. We're going to see this in another example. Why did I want to do this? I wanted to do this basically to have the name of the object, and because now we can go to another ESA sky. So we can go to another VO tool. Sorry, when I say VO tool, I refer to any tool which uses virtual observatory technology. So
Simbad, what it's doing behind the scenes is querying its own database. Now we move to another one, which is called ESA Sky, and you probably saw how easy it was to get there. So you basically Google, if you don't have access to Google, you just use your favorite research engine. You go ESA Sky INT, and is normally the first entry. You go there. This is managed by the European Space Agency. And you choose if you want to do science or explorer. Normally, well, as a scientist, I prefer the science part. And normally it shows you something pretty and funny at the entry point. This normally, as far as I understand, is random. But you can search your favorite object. So in this case, we're going to search for M51. So I type in M51, I click on enter. And now it is resolving the image of the object. So what it is actually doing, this is asking through a virtual observatory protocol, which is called CAP, is querying the image and is getting the image and is showing it to us. And it's using Aladdin for this. We're going to speak about Aladdin in a sec. And this is the Whirlpool Galaxy in all its beauty. And so I want to make before making a game, I want to show you the real scientific power of ESA Sky together with the virtual observatory. So you can see that there's these small icons on the upper left. So this first one is which image observations we have about this area of the sky. And we have images from we actually have several images from JWST, Hubble Space Telescope, both in optical and near infrared. We also have a Hubble in the ultraviolet. We have Chandra X-rays, blah. I will enter in this again in a second in a little bit more detail. Then we have a lot of objects as catalogs. So actually in this region, since it was mentioned before, we also have Lamost spectra. I didn't know. See, you always learn something. And then again, you can check if there are spectra and light curves in this area. And again, you have Lamost spectra of this area of the sky, and you have Herschel spectra, you have JWST spectra. And let me close this. And then you can actually start doing funny things. You can check if there are multi-messenger events in this area of the sky ever recorded. And I will close it for the time being. What I really want to show you about this, because it can also be interesting for the ones of us who do outreach or lecturing, is that what you're looking at here is, you see it up here, is DSS2. DSS is the digitized sky survey. So these were photographic plates and these were digitized. And you can actually check, the first icon on the left, it shows you can select which sky you want to look at. So let's stick to optical. And I want to show you that I can actually look at this as I can check what is the color image from pan-stars. And yeah, the alignment didn't come up particularly well, but you can see that pan-stars go significantly fainter than DSS. And you can start checking different surveys or different images. For example, you can check SDSS. And yes, the color image from SDSS is significantly prettier. And then you can start wondering, oh, right, so this is a beautiful galaxy, right? We agree it's a beautiful galaxy. Mm-hmm. And people are nodding here in case. And you can go to near infrared. And in the near infrared, you can start to look at it in 2 mass. So all of a sudden, you start losing the emission from the bright stars, right? So this is 2 mass, and you can check if it has been observed by others. For example, you can check the observations done with NICMOS. NICMOS has a very small array, right? So this is the small observation that with NICMOS. You can barely see anything, but you could, and let me show you a superpower. So you can zoom in, you can click on this small wheel, and then you can change the stretch. You can use the hyperbolic arcosine, and then you can change the color cuts. And I'm always very bad at this. The other day with square root was working better. So you can start seeing again some structure here. Then perhaps you can move to mid-infrared. And here now you have all wise, right? And now you have the image in all wise. You're starting to lose spatial resolution, and you have lost, basically by now you already have lost a lot of stars. And again, you have a lot of missions you can choose from. I just don't want to spend the whole time here speaking about this. You can move to the far infrared. By now, this is only dust emission. And then obviously, what I would, if it was me, I would just go back to the optical, and then I would just ask myself, okay, so now I can go to the more energetic part of the spectrum. So I can go to ultraviolet. And you can see in Galaxy, this is now most of the hot stars, right? Emission. And I guess by now you have, you understand the game, move to soft X-rays, and this is XMM, but you can also choose Chandra, for example. And you can see the beautiful spatial resolution of Chandra. So the one game that you can play, and this is the last thing I want to show you using this, is that you can actually now start going bandwidth by bandwidth. So this is soft X-rays, and you can add a new one. So you can do ultraviolet. Then you can add Sloan. I'm perhaps going a little bit fast, but I hope it's basically clicking on the plus sign down here. And then you go to near infrared. Then you add the mid infrared. It's basically all those things are things that I'm liking. So I'm sort of like I'm liking the default. Mid infrared and far infrared, I'm stopping here. And now you can just play the movie. And you can see how it changes as you move along wavelengths. And for outreach and for education, I think this is fantastic. That the images are already aligned, and it is. I find it difficult to explain how fantastic this is to people, to younglings, because if you had to do this 20 years ago, 15 years ago, you would have to get each of these images, astrometrize them, align them, make the whole thing by yourself. It will probably take a few days. And now it took us 3 minutes. Now, sorry, I have my notes on my mobile, and obviously my mobile has kicked me out. Now, I may want to do a similar game since someone mentioned Nova before. Let's go and do a similar game with the recurrent nova, which should not be named, which is T-Pixidis. That's my obsession. And so T-Pixidis, we go, if we go to the to Simbad, we get the coordinates, and we find out that it's a variable star, it's a nova, it's a cataclysmic variable, it's a blue emitter, and I honestly don't remember what HS means. And it's a near infrared emitter. Thanks. And now, since I have to do this, I will have to do this for the paper that I'm writing. So let's go and check this part down here in the bottom left. So you see here, you can also see a small image of the field of the star. But one of the most powerful things is this small rectangle in the lower right, which says photometry within 5 arc seconds. So if you click on photometry within 5 arc seconds, what this is now doing is, again, because the virtual observatory allows to do this, it is querying all the catalogs, photometric catalogs, which provide photometric information within 5 arc seconds from the position of the object. This is what we call simple cone search, what Shenshen was mentioning before. It's one of the 4 or 5 important protocols of the virtual observatory. So what? Please don't make me do this. The site can be reached. Come on. So if the site can be reached, it will get all the photometry from the different catalogs. So we'll get photometry from Tomasi, we'll get photometry from Weiss, we'll get photometry from Gaia. And if it doesn't work, it doesn't work. All right, it doesn't work. It's all right. I'll pretend.
The link on the shot.
Yeah. That's that. No, the I have no idea why it's not working, but yeah, we will ignore it. We will ignore this issue. This never happened, even if it's been recorded. And we can use this as an example for something else. So I want to show you some tools from the Spanish Virtual Observatory, not only because the head of the Spanish Virtual Observatory, Enrique Solano, is a good friend. Actually, he introduced me to my wife, so I owe him a great deal of affection. So once you go to the Spanish Virtual Observatory, they have a series of tools and services, and a lot of them are very useful, very interesting. And I want to show you 2 services here today. One is, if I see it, the discovery tool. So I'm clicking on it, and so you can give a list of object names. So in this case, I'm only giving one name, and it's TPX. Within 5 arc seconds, I want to get all the VO services which provide images, spectra, all the physical parameters available from Vizier, and we'll speak about photometry in another moment. And then I will not ask for Gaia because we're going to see Gaia in a moment. So if I submit the query, what this is now doing is, and actually you have the status bar here. This is querying the different services that in the virtual observatory deliver images and spectra eventually. And if it doesn't do it, I will go, all right. So it is doing it. So it's just takes a little bit of time. So what is happening behind the scenes is this is making a series of requests. So these requests are literally through URL requests. It's literally as if you are asking. No, it's literally a URL. So literally is as if you're asking for any website. And to some extent, what it is this is the core of the virtual observatory, the fact that you basically don't have to worry about, as a user, as a data provider. So Shenshen is Shenshen's problem, and it has been my problem to provide the data. But then once you are a VO user, you just ask one tool, in this case, the discovery tool of the virtual observatory or of the Spanish virtual observatory, or ESA Sky, and ESA Sky just sends this URL to the service. The service receives the URL and says, "All right, thanks for asking," and replies with another URL. At the end, there is a standardized communication form, which at the end is a VO table. A VO table is an XML file, and I'm not sure if I'm getting too technical, but basically is a way to compact all the information and pass it on. And then the tool interprets it for you. So you don't have to worry about what is the URL that I'm supposed to write, what is the content of the VO table that I'm getting. The tool does it for you eventually. Since there are many tools, and since we are hopping through different continents, it may take some time, and we are almost done. And the important thing is, at the end of the day, once you have done the whole job, you can actually retrieve and download all this information to your computer. You can see down here, you can download you will be able to download the parameters as a CSV file, or you will be able to download them as a VO table, which again, we just said is an XML file. And I'm going to speak about this SAMP hub in a second. This is going to be so much fun. And let's hope it finishes and shows up everything.
Tried the documentary from China, but it's also not working.
All right. So the important thing is, if it was us doing it by hand, we would have to remember to which service I want to ask, and then right. So I have to ask to the Chinese VO, to the SDSCI service, to whatever service, and then I would have to take care of all the problems and mistakes and no service not working, service down, service is replying in one way, but now everything is standardized, so you immediately get all the information, and again, the tool takes care of all the exceptions and problems. And so you can see down here, this is ANOVA, so yeah, you don't get effective temperature, log G, because it's a binary star. You have 11 services which provide the spectra, and you have different services which provide these are the different services which provide spectra, and I may look at the services which provide images if I want to. But I don't want to, because what I want to do is to move on and show you Aladdin. So let me move on to Aladdin. And I'm not kidding. I'm pretty sure you can see my desktop. So, and I didn't do anything special for this session. You can see two icons here on my bar. One is Aladdin and the other one is Top Cat. And this is just to show you that I'm not cheating. This is literally what I do almost on a daily basis. So let's open Aladdin. If you don't have Aladdin installed, again, this is as easy as to look for Aladdin Astronomy, and you're sent to the web page of Aladdin Sky Atlas. Since it was developed in Strasbourg, probably the correct pronunciation would be Aladdin. I still call it Aladdin. There's several versions. There's the desktop version. There's the light version. Oh, I didn't know that there was iPi Aladdin. This is interesting. So the Aladdin Lite is particularly useful if you have your own web page or your website. So what I showed you on ESA Sky, that was powered by Aladdin Lite. If you have seen the preview of the LSST images, that was Aladdin Lite. So most of us who show images on our websites or our data centers, most of us use Aladdin Lite. But I'm going to show you Aladdin Desktop. So I already have it. I don't have to download it. So you launch it, and this is the entry screen. And let me show you something very, very, very fast. So I can.
So you are download Aladdin Lite.
No, I download Aladdin, the real thing.
There's people says that it's not a working for Mac version in the Zoom.
All right. So my question is not working. Is that? Oh, it is available for Linux. So all right. So for Linux you have to install. Oh, right. For Linux you have to install. For Mac, there is a famous problem, which is addressed somewhere. Let me see if I will reply about the Mac issue in a moment. But it is a famous issue, and I will comment on it when I think I know the solution for Top Cat, and it's the same solution for Aladdin. So what I want to show you here is I want to use the revised new general catalog. Right. So most of us, the people who entered astronomy and because they liked astronomy as kids, yeah, that was my case. So we started and we all heard about the Messier catalog, and then we heard about the NGC, the new general catalog. And now there's a new version, which is the revised, the new general catalog. And, you have this beautiful distribution of objects. Sorry, and I just want to show you again how I did it. So I entered Aladdin, and Aladdin is split between the catalogs that you can access, or the services, actually, more correct, the services that you can access here on the left, your working area in the center, and the status on the right. So what I did was here I asked to select everything which was named revised, the new genera, and I didn't even need to write the whole thing. It already knew what I was looking for. And if I just delete it, it shows everything which has available. So, and just to show you, it has available images split between wavelength, databases, catalogs, data cubes, ancillary data, outreach data, also deprecated data, because why not? And so I downloaded all the data from this catalog, and if I go here on the right, I can see that I have about 8,000 sources. And these sources are distributed all around the sky. This is the in height of projection and is equatorial coordinates. So to look at a catalog like this is a little bit cold. So let's give a little bit of soul to it. So if I can go to optical, and I like to use this Mellinger color picture. And this is a picture of the whole sky. And now you can see the plane of the Milky Way. And I can also add a grid, coordinate grid. You can probably see it now. So, and I can open this a bit more, and I can zoom in a little bit. So we can start to see what we're looking at. As expected, this is mostly extragalactic stuff. So obviously in the plane of the Milky Way, we have less things with respect to out of the plane of the Milky Way. And with this arrow on the top right, I can select one of the objects, and with pan, I can start moving the image around. I can also move the image around using this zoomed out version of the sky on the lower right. And if you look at the whole sky here, you see that there is a big concentration of objects at the bottom left, right? So let's move that region in the middle and try to figure out what we're looking at. Let's zoom in. And some of you will have already recognized it, especially the people living in the Southern Hemisphere. So that block of objects, that was the Large Magellanic Cloud. The other object is the other object here is a Small Magellanic Cloud. And just out of curiosity, let me check. It's 5 hours of right ascension. So if you go out one of these nights and the sky is letting you look up, towards the end of the night, you may actually be able to see the Magellanic Clouds. It's a nice romantic thing to do. Right. And one thing that you can actually do now is now I can zoom on the Large Magellanic Cloud, and you can see in here that now I still have 8,000 objects visible, but I'm sorry, I'm trying to move the zoom panel out of my way. I can select the objects in the view. I can open TopCat. And now I can do the magic. I'm sorry, I get too excited about this. So what I can do is, and say, rip up. Not so first I want to do this. Epa. Is it just selected already? Select all objects, select all objects and select the place. No, it's all right. So I want to send these ones to TopCat, and I'm sending them. And ta-da! No, I don't. I sent all the 8,000 objects. I made a mistake. You will forgive me in the interest of time. So now I have all these objects important in TopCat, and TopCat is beautiful tool to analyze tables. So how do I install TopCat? Again, let's go back to a browser, TopCat Astronomy. And TopCat is, you believe it or not, TopCat is written and maintained by one person who is who's possibly one of the most valuable people in astronomy. Without him, like 80% of science would stop happening. So if you want to install it, you just go to downloads, and here you can download for the jar file, which is going to work on any operative system, the Mac OS, and here it should say you're advised to download using curl, and this is probably the problem that people were having also with Aladdin. You're probably going to get that the DMG file is damaged or can't be opened. So there is a fix, which is you're supposed to do this X ATTR minus D whatever, and instead of TopCat, you're supposed to use you can do it for TopCat and you can do it for Aladdin, and then it will work. It's unfortunate. Eventually, it may be fixed, but this is the workaround. So once you open it, once you have it, TopCat is a beautiful tool to analyze tables, and it literally allows you to go about tables. And the most important buttons at the beginning are these three ones. Actually, this one and this one. So this one here, which says display cell tables, display cell data, doesn't it? Yeah, display table cell data. It shows the content of your table. So it has the name of the object, the coordinates, various systems, magnitude, whatever. There is this other button here, which is display column metadata, which has the name of the column, the units of the color, the type of the color, if it's a double, if it's an integer, if it's a short, if it's a character, if it's a string. And this is going to be super important, not much for us now using TopCat, but later when we will use Python, knowing what type of variable, what type of data you have in a column, that is going to be super important. And then you can start doing, for example, you can start doing histograms. Like histogram in magnitudes, or you can make a scatter plot. Like you can go, it doesn't have the size, not too bad. You can make histograms. Could have done smarter histogram. And you can make cross matches with other catalogs. So instead of doing a cross match, a small cross match, let me do something crazy. Let me cross match this with the whole Simbad. We said that Simbad has millions of objects. So if it was during my PhD, I would have had to do a script. I would have done it in Fortran because that was available in the good old days. And I would have to go line by line through the 8,000 objects of my catalog, compare with the 20,000 objects available in Simbad, and check if everything was available. It would have taken a lot of time to write it, and would have taken a lot of time to run. So in this case, I can use a service. Again, this is completely view. And I can just say, I want this catalog. These columns are the coordinates. Within 1 arcsecond, just give me whatever you have within arcseconds. Go, do it for me. And it only delivers 38 rows, probably because I'm using a too small of let me do it a bit bigger. Let me remove this. So yeah, in this case, we got 362 rows. And again, first thing to do whenever you get a new collection of data, you go and see what you have in the columns. So in this case, we have the original columns, and now we have the columns which come from Simbad. So we have the coordinates, we have the types, and we're supposed to have some, we have morphological type, we're supposed to have the size, which I cannot see now. Major axis, yes. No, major axis or positioner. I thought we had the size. Anyway, if we don't have the size, I will do size major axis here. All right, so again, said I wanted to do a decent, I wanted to play a game. So this is, let me show you the magnitude in the x-axis and the size in the y-axis. Basically, what am I discovering? I'm discovering that for brighter objects, the object is bigger. Sort of makes sense, right? So it's probably a galaxy or whatever extended. It's bigger when it's closer. So I would just want to make, all right, halfway through. I'm roughly where I was hoping to be. So let's play another game, and this time we're going to play something even more fun. The little planes, delete this catalog, delete this other catalog. So this time we're going to go and we're just going to go crazy because we can. So we heard about Lamost, right? So if I can type Lamost. So Lamost, and you can see that we have available here several data releases of Lamost. So the last one that I see here is DR7, and let's check Lamost low resolution spectroscopy general catalog. This is a lot of stuff. So instead of downloading a lot of stuff, I want to download this thing. Mock is, if it downloads well, yes. Mock is a very powerful tool that I don't think we have touched upon already. Is the multi-order coverage map. It basically allows you to have, and let me zoom out a bit just. I'm sorry. it allows you to have a visualization of the area which is covered by a survey. So you have a feeling of what is the sky area which has been observed. So in this case, LAMOST is based in China. The telescope is based in China. So as you would expect, the LAMOST footprint doesn't cover the southern hemisphere. People from Brazil and from South Africa now have a small tear in their eye, which I understand. But we keep playing. So now that we have LAMOST, and Shanshan was already mentioning also the other big spectroscopic survey, which is SDSS, which is the US LAMOST, or LAMOST is the Chinese SDSS, right? It's like, so if maybe if I have to write Sloan, right. Now the Sloan Digital Sky Survey is I have here SDSS data is 16. I just wanted, all right, let's just keep things easy. And let's download again. Let's download only the mock. So I download the mock of Sloan, and now you can see that Sloan is observing in one way, LAMOST is observing another way. So you can see these two different ways of observing the sky. Also, you can see the science goal of the two different surveys is very different, right? If I understand correctly, LAMOST is more stellar, and Sloan was born as a quasar survey. So obviously, and now we're going to, again, this is because I am me. I always feel like I like to use the visual help of the Mellinger projection beneath so that I can have this visualization. So you can see now that I have the Mellinger projection under, you can see where is the Milky Way going through. And actually I can switch on or off the different planes just by clicking on them. So if I have now the Mellinger image with the Milky Way beautifully passing through the sky, and I overlay only the SDSS mock, you can see that the SDSS neatly avoids the plane of the Milky Way. But if I now remove SDSS and I only add LAMOST, you can see the LAMOST covers very much everything. Arguably, this part here is a bit complicated, so we accept that this part is ignored. And all this story, in all this story, I want to add another complication because I can. And I want to add the catalog from Ritter and Kolb about cataclysmic variables. Sorry, probably only with Ritter is enough. And it's, yes, it's this one up here. And I can just download all the data because it's only a few hundred objects. And let me remove the surveys. So these are the cataclysmic variables from, cataclysmic binaries from this very famous catalog. They're spread all around the sky. And now we have all these sources. We have these two surveys, and let's go and check if we can do something. So first thing I want to try to do is to find what are the sky regions which are covered both from Sloan and LAMOST. So let's go and we have this coverage property up here. and I can do, if I'm not mistaken, is with logical operation. I can specify 1 or 2 mock planes. So I select one mock which is SDSS, the other mock which is LaMost. I want to have the intersection, and I create it. Now, and you can see now in yellow, sorry. And now I can see in yellow, this is the area which is covered by both surveys. And now we really want to play. So now we want to get all the objects, all the cataclysmic variables from Ritter and Kolb, which are in the footprint of both surveys. Doesn't guarantee that we're going to have spectra from both surveys, though, right? So what we can do here is we go to coverage and we filter a table by mock. So the mock plane is this new one that we just created, which is called int. Actually, I can do something better. Let me show you something even nicer. So I can actually go here. Sorry, I click on the plane, and I right click. I go to properties, and I can change the name, and I call it intersection mock. Apply. So now that I go to coverage and I do filter table by mock, this is a decent name, right? So intersection mock. And what is the catalog that I want to filter is this one, which is called CP data. And I want the objects which are inside, create. In a blink of an eye, we already have it. And we have 159 objects which are inside the our area. So again, what I can do is I can take this and I can send it to TopCat. Remember that I commented when we were looking at the SBO discovery tool that there was this SAMP protocol. SAMP is the protocol which allows us to move a table from one service to another. Couldn't I take this table, download it to my computer, and then upload it to TopCat? Sure, I could. Is it the most efficient way to do it? Not necessarily. With this way of communication, I preserve all the information. I never have information loss. If I download it to my computer, for example, if I download the data as a CSV, I may lose some metadata. This way, I don't lose anything. So anyway, let's go to TopCat now. I have this data, and again, I want to see what are the columns that are available. And this is everything that is the Ritter and Kolb catalog give me, right? The name of the object, the coordinates as a string, but since I downloaded it through Vizier, I also have the coordinates in decent units, so in degrees. I have the type. I have the orbital period. I have the spectral type of the 2 stars. All this complication, and I just want to do one thing. The TopCat doesn't like this point in the name, so I have to remove this point because I just want to do one thing. So for the people working on cataclysmic variables in here, they feel the need, whenever they have a bunch of CVs, they feel the need to see the period histogram. So I need to see this. This is literally my working tool, and I need to see this in hours. and I need to see this. Right, sorry. Got excited, and plus I do this literally every day. So you can take a column that you're using for display purposes. So in this case, I'm only selecting the orbital period, and you can make arithmetic operations. Like in this case, I multiply, since it was in days, I'm multiplying by 24 so that I have it in hours. But then I can go and I can ask the axis to be in logarithmic. So I can get the x-axis and ding, all of a sudden this is in logarithmic units. I can rescale with this thing up, and you can see what you can see that this looks like a decent population of cataclysmic variables, because you have the period minimum at about 78 minutes, you have the period gap between 2 and 3 hours, and you have the normal period distribution. I could also, I'm not going to need it now, but I could also get the y-axis in logarithmic, so just by clicking on this, but I'm not going to need it now. There's other properties that we're going to need in a moment. So if I display now the objects, I can start looking at the objects and see what we have here. And you can see there's one column which is type. So I can ask it to sort up or down the type. So like this is going to be easier because it's going to cluster all together the different objects. And I already know that I'm going to be happy. So, and I actually sorted it the other way around. I always get the sorting wrong. So anyway, sometimes some types are more useful than others. Like empty type is not particularly useful. Type cataclysmic variable is not particularly useful, but we have a lot of dwarf novae, we have a lot of nova likes. For the friend who was asking about novae, we're going to speak about this beauty here, which is GK Nova Persei 1901. And I'm going to and I can select a series of objects. Like, for example, I can select all the novae that we have in here, and I can go up here, and there's this button which says define a new row subset containing all the selected rows. So I select this, I create a new subset called novae. And actually, if you now go back to the histogram, you already have the position of the novae in the period histogram. And you see that they are where they're supposed to be. So I'm going to hitchhike my own explanation to ask for help from Shenshen, because now is when I want to see if we can get the spectra from these 5 stars. I have no idea how to do it. So I guess I would go to VO, I would go to simple spectral access. I would look for Lamoste here. Survey spectra. This is my guess. I cannot go. All right, so I'll just go with object name. I'll just go with GK per. Has resolved it, and 5 seconds. Do I have to select any specific spectrum format?
I don't think so. Maybe leave it blank.
I'll leave it blank. All right, I'll leave it blank. Go OK. I'm cheating a little bit because I already know that this is going to work. Oops. I think my top got half crashed because now it's not showing anything here. Actually, no, it's not a lot of data. So I think it's somehow just crashed. Let me do something. Let me restart TopCat. If it works, it works. If it doesn't work, this was an extra also for me to learn something new. So let's do it again. So this is simple spectral access. We said we wanted the most. Tier 5. GPPA. Within 5 seconds, I'm sure that there's not. All right, here we go. There's one row. And if I look at it, sorry, let's look at it like this. This is their beautiful work. I don't want to take any credit for something that I have not done. And but now I need your help to. How do I download the spectrum? Or I just go to the website.
Yeah, I think maybe this is only for the catalog.
Okay.
Yeah.
Oops. All right. If it's just URL to view for a preview of the dataset. That looks fun. So let's go to this URL. Ay, qué cosina bonita.
Yeah. I think we should fix this because this is too small.
It looks like a spectrum though.
Yeah, there's a mode.
Okay,
Is it the right?
Is it? I'm going to try this one. Oops. Okay, this is a view table. So you just downloaded a view table to my computer. No, it's trying to download a view table. Downloading secure file. Aha. Don't we like danger? Downloads. It's called Lamos, blah, blah, blah. You're seeing all the
Lamos. Yeah.
For the people at home, it is so much fun to see Shen pointing at her computer saying, "It is here." All right, so yes, we have a spectrum here. So for whoever asked this is a spectrum. So you see this is wavelength, this is flux, and this is flux error. And so basically now you can go here and a spectrum at the end is, here it goes. Actually, you can do it a little bit prettier. Add line. And you can remove the points. And you can see this is clearly H alpha. This, if I'm not mistaken, is helium. And sorry, and you can zoom in l'allero. Actually, I prefer to zoom in like this. Minimum max 3,700 and maximum max 5,200. And yes, this is H delta, this is H gamma, this is H beta. So yeah, basically, yes, we got a spectrum. and you can open it with, then you can open it with IRAF, you can open it with your favorite. Yeah, I learned something new myself. See, so the last thing that I wanted to show you is I want to show you possibly the most powerful thing that you can possibly do within the virtual observatory, which is to use SQL. SQL is the what is the S for? Structured query language. Structured query language. And there's I'm going to just show you two easy approaches. So I'm going to show you an approach, something with Simbad. Again, we're going to keep it simple. You remember when I showed you with Simbad before, you can see that within Simbad, you can see the type of an object. So I want to download all the objects which within Simbad are cataclysmic variables. And you may remember, I still have it open here with TPX. The object names, they're not particularly, they sort of make sense once you get used to it, right? No for Nova, CV for cataclysmic variables. But you have to learn them. How you learn them? Well, there's this button here, object types. And if you click on it, it opens you everything it has. So you can start to go like different set of stars, different taxonomy of stars, sets of galaxies, and you can click here and you can say cataclysmic variant. Cataclysmic variant here. It's CV star. Oh, nice. And now, with this important piece of information, we go to the TAP service. Sorry, I just want to make sure I emphasize it enough. It's on this button here, which says TAP. TAP stands for Table Access Protocol. It's, again, another one of these beautiful protocols. And once you start playing with TAP, once you start playing with a database, the first thing you have to do is to look at the structure of the database, because you have to figure out what is the table that you want to query. You may want to query several tables. For this example, we're only query one table. We're not going to join tables. We're going to just keep it simple. They have a cheat sheet, which is also super very useful. And they have this button here, which is the Simbad tables, which is this beautiful image where you can navigate all the tables which are available here. And the table that we're going to care for is this one called basic, which sort of makes sense. We're going to do something basic. So do me a favor and never, ever, ever go and download everything. So the way I'm a self-taught SQL user. Although my database engineers at home, they have been helping me a lot, but it was mostly for me trial and error, and every now and then they would come to me like, "You're being ridiculous. You do this properly. You do it like this." So what I normally do is I first go like, all right, so I want to get the data from a table called basic. And I want to get, here is where you select which columns you get. And if I were to select star, this means select everything from the table called basic. Never do it. Please don't do it. The only time I allow you to do it is when you do select only the first 10 rows from this column, which is when you do it to start learning about the table. So you can, in this case, I allow you to do it, and you do it, and you get these first tables, so you have a feeling of what the table looks like, right? But then what you really want to do is then you, actually, let me do it again. And then you go like, okay, so actually what I really want to do, I only care for the main ID, the object type, red ascension, and declination. So actually, so you can remove the star and you can go like main ID, array, deck, and O type. All right. And now we only want the cataclysmic variables. So we want the objects which are for where O type equals CV star. And this should work. Unknown columns, what do you mean unknown column? See, I said it should. Ta-da! And I can actually remove now, I can remove my top 10 to start. And it gives me, this is all the objects which in Simbad, they are cataclysmic variables. I can say that instead of getting format the output as a text, I can get a FITS, so I can actually download it to my laptop. Actually did it a few months ago because this is, again, is what I do. And to finish on a high note, I want to finish by showing you Gaia. So Gaia archive, and here it goes in all its beauty. This is the archive of the European Space Agency with the data from the third data release of Gaia. And you can access in this search tab, and you can do a basic search. Again, on the day, actually on the first day of every data release, this is what I've done. I entered and I typed tpix, and I submitted a query to get to see what was the parallax, which is somewhere. What I want to show you, actually, no, I can do something. Submit query real quick. So all the objects in Gaia, they have a designation, which is this super long name, which is actually this source ID. And you can see here, there's this beautiful tab called single object. And you can put your source ID here, and you get the astrometric information of your favorite object. You can see the parallax of tpix in this case. You can get the photometric information, the astrophysical parameters. If it has epoch photometry, you will find it here. If it has spectra, you'll find it here. And then here you get the multiple star classifier, the single star classifier, right? What I don't want to do, because we only have 10 minutes left, I just want to make a super simple, by my standards, a super simple query. And I just want to show you the color manual diagram of nearby stars. So, as I said, the first thing you have to do is to go and see what table do you want to use. And Gaia also gives it away. Once you open the ADQL query, you already have Gaia source or Gaia source light. Let's use Gaia source light. So from Gaia source light, as DR3. Actually, I don't need this. So what do I want? What do I want to get? Let's do again, select top 10 star. And submit, and it's going to hate me. So if I submit, then I get here the result. It was very, very fast, again, because it's only 10. And here you have job information. Here you can download the results. You can display the top 2000 results. And here, since I only asked for 10, here is the top 10 results. So I can see that, yes, it displays a lot of information. We don't need to get into all the information from Gaia now. But, and you will forgive me, but I have part of the job I have already done it for myself. So I know that I want the source ID, right ascension, declination, and all right, for the time, and I want the BP. So you may or may not, hopefully by now you know, if you're a stellar astronomer, you must have touched Gaia. So Gaia observes mostly almost in white light, is what they call the G band. And then it has two very low resolution spectrographs, which they're called the blue photometer and the red photometer. Once you combine all that light from those spectrographs, you get the B photometry and the red photometry. And you can get a B minus P color, sorry, B minus R color. And then you can get the G band photometry. And since we are at it, we can also get the parallax. So in this case now, we're only focusing on, I'm just submitting the query just to show you that now we are only getting the columns that we care for, right? So source ID, red ascension, declination, BP minus RP, G band photometry, and the parallax. Now, this is not enough to be able to tell if these are, sorry, this is not enough to do a color minor diagram, right? So we want to select the objects. And how do we select it? So we do go where, and forgive me, but I have already done this. So parallax over error larger than 10. This means that the signal to noise of the parallax is larger than 10. This means, according to Xavier Lurie and collaborators 2018, that we can invert the parallax and get a distance. Parallax larger than 20, it means that the object is nearby. Don't make me do the number now of how many, within how many parsecs it is. And then photometry, and then G band photometry larger than less than 18, it means that it's brighter than 18, right? So I can actually, I can show you something. I can show you another powerful thing, which I'm not sure if it works like this. I can actually count how many objects there are. And no, it failed, because to count, I'm only supposed to count one column. And hopefully will not take too long. Right. So we count is a function within ADQL, and basically what it does is counts how many different source IDs we have. In this case, I'm going to show you, and we only have 38,000 objects. And so let's go back to what we had before. Submit query. So now we have these 38,000 objects. And here we have the parallax, we have the G magnitude, and we have the BP minus RP color. And what I can do is I can download this table as a feeds, and I can download it to my computer, which is happening now. One download in progress. And if everything goes well, actually, now I have the doubt. Can't I just send it? No, not atomic. It would make sense that I would be able to send it through SAMP. Anyway, has been downloaded, so I will load it. I'm sorry, the names are always very, very funny. So it's the 17 blah blah blah. So you see, I uploaded it. It's 38,000 columns, 38,000 rows, 6 columns. We can look at the columns. Sorry, we can look at the table. I'm not going to spend much time looking at the table, but we can make a scatter plot. In the x-axis, I can put the BP minus RP. In the y-axis, I'm going to put the G band, and now I can flip the y-axis. This doesn't look like a proper column-linear diagram, right? Why? Because this is not the absolute magnitude yet. So let's do the absolute magnitude. So plus 5 minus 5 times logarithm 10 of 1000 divided parallax. And in all its beauty, this is the column-linear diagram of all the stars within, I can't remember how many megaparsec, within how many parsecs. We can actually even look at the parallax distribution. We can actually do 1000 divided parallax. This is 50 parsecs. And so perhaps I've been going a little bit too fast, but I've been trying to cover things that you can do with SIMBAD to explore an object. ESA Sky to explore an object and a sky region. TopCat and Aladdin to discover a database and to explore a database within space and also within colors. Actually, speaking about within colors, there's something else that you can do. You can actually select a region of your colored linear diagram, like a region in your scatter plot. You can select this and you can say, okay, so now I want this to be a new subset, and you can call it funny. And now you have this subset, which is funny. It's only 149 objects, and you can actually go and check on SIMBAD what are these funny objects within 3 arcseconds. And now you have that 59 of these objects, they are in SIMBAD. And you can look at them and you can see what they are, what is their type. So there's high problem motion stars, you have a white dwarf, and let me show you a trick. You can remove, you can remove things that you don't need so that the visualization of the table is better. So object type is here. You can see that you have l'allero. And yes, and we have a cataclysmic variable. Woohoo! Sorry. So again, so we've seen how to analyze catalogs, filtered by mock, cross-match big catalogs. We've discovered how to get Lamoste spectra. I hope this was useful, and I'm sorry if I'm not leaving too much time for questions, but if you have questions, go away. Well, sorry, go away. I'm tired. I'm tired. It's been 1.5 hours at full speed. Shoot away.
There's some questions, I think. I try to answer some, but
You're too kind.
yeah, I think you can cross the, yeah.
Sorry, let me go up. All right. This seems like a cool thing to deep dive into. Is this type what format is it in? See, right. The inside TopCat uses VO tables, but you can then work with it in CSV, FITS, ASCII, extended CSV, and tables, tabular separated for tabular separated values. There's a stupid amount of, actually I can show you here. All of these are available. There's some of these that I don't even know what they are. Does this work for GRB catalogs too? So if I want to check all the GRBs for respectively the supernova along with T90 and Redshift, then can I find it here either in Aladdin or TopCat? I am not sure. I should check. I'm not sure. I wouldn't bet my house on it. The fix on TopCat, it fixes on Aladdin. Well, at least in my experience, it does. For the GRB question, I will try to answer you this afternoon. TopCat's feature shares. No, sorry, this was.
Yeah, I tried to answer the question about the TopCat and the pandas. Yeah.
Right.
Similarity. Yeah.
So actually, this is something that I want to comment. I wanted to comment, and I bet that Shenshen's comment was along this line. So bio tools are beautiful, and TopCat and Aladdin are super beautiful and super nice to play with. I wouldn't, if I can give a piece of advice, I wouldn't use the workflow on Aladdin and TopCat for the writing of the paper. So if you're writing a paper, what I would do it is I would use TopCat and Aladdin for something quick, like, all right, so I want to make sure that, or are there cataclysmic variables within this selection with it real quick? Yes, cool. Okay, so now that we have this selection, now we go to Python, and then you do the whole workflow in Python, and you do it properly in Python. Why this? Because once now I close TopCat, everything is gone. I can save the session, but most of the way that I selected the region, that is gone, and that is not reproducible. So if you want to have something which is strongly and reproducible, which is one of the cores of VO and the cores of current data analysis in astronomy, then I advise you to do it in Python.
I think we have more time to learn how to use the Aladdin Tomcat and even Python this afternoon.
Yeah,
Yeah.
yeah.
And there's, I think there's another question. How to improve the
How improve my SQL on Aladdin? Oh my goodness. If I'm not mistaken, Aladdin does not support SQL queries. If you refer to improve your skills, the best way to improve using Aladdin is by using it. What I normally do, I give myself tasks, say, okay, so today I'm going to play around and I'm going to try to do this. There is a lot of resources anyway on the website of the International View Alliance. There's a lot of VO schools organized by the various national virtual observatories. I know that the Spanish Virtual Observatory organizes at least one school per year, normally 2 or 3. I'm not sure if the Chinese Virtual Observatory organizes.
training? Yeah.
So if you want to improve your skills with Aladdin, I suggest you get in touch with your national virtual observatory. If you want to improve your skills with SQL, the easy way is to suffer through Gaia. Gaia it's funny. Gaia has 1.8 billion sources, but from my perspective, it has become the easy way to do it. Basically, because most of the information is in one table. So you play with, if I wanted to improve my skills with SQL, I would probably play with Gaia and with Simbad. And these two are very nice entry level.
Yeah, I'm not sure if this is the right way, but currently we provide with the Lamos data, they can put their search criteria and to generate SQL code. Yeah, and they can do the things right now.
And in most of the most of the ADQL services, like, so I'm opening Topcat now. And if I try to look for Gaia here, I want the real Gaia, which is ESOTAP, this one. Use service. And the important thing is most of them, they have examples. So you can come here and you can say, where is it? Gaia. I'm in the wrong one. Anyway, so let's pick up a random. So I can just come here and say, okay, so I just want to find out the objects within this box. And you just look at the examples, play around with the examples, fail, and then you will slowly you improve. Oh, and this is because because this was the ESO and not the ESA. Sorry, got one letter wrong.
I think it's time for lunch.
Yeah, I think it's time for lunch. Then this afternoon we go back with more Aladdin and Topcat and Python.
After an hour.
All right, so we reconvene in 1 hour. Okay. I will stop sharing. And see you guys later.
Okay.
See you guys later.